Alrighty, so away we go. Section 8.3, all about hyperbolas. You studied hyperbolas a little heavily in chapter 8 in Algebra 2, but very different than what we're going to see here. What we get is a super nice way to work with them. Now, hyperbolas have a lot of nice little short formulas. We're not talking nice little short formula here, but we are talking, looks a lot like ellipses, looks a lot like the other conics. And pretty obviously, the hyperbolas we're going to be working with are the ones that are really nice and perfect. You know, that's the nice thing about this particular formula for conics is that we get everything super perfect and nice. So we get a good feeling as we're doing the math. Hey, that worked out nice. That has to be what this is. So we're going to understand the geometry of hyperbolas and the key features. And we're going to talk about writing equations for hyperbolas and then, of course, translating right, left, up, down, and eventually applications of hyperbolas, which means our little word problem pieces of all that. So the geometry of a hyperbola. A hyperbola is a set of all points in a plane whose distance from two fixed points in the plane has a constant. We have seen all of this word for word when we talked about an ellipse. It's that last word that changes this up. With an ellipse, it was a constant sum. We added them together and that sum stayed the same when you were on any point on that ellipse. With hyperbolas, there it is. There's our subtraction right there. The difference between the two. So the fixed points are, of course, called foci. Again, some people pronounce it foci. Focus, when you have two foci, just makes more sense to me. So it's one of those things that is pronounced two different ways, like neither and neither. The line through the foci is the focal axis. The point on the focal axis midway between the foci is the center. The points where the hyperbola intersect its focal axis are the vertices of the hyperbola. Now here's where it gets weird, because technically there is no name for the covertices of a hyperbola. It's just one of those things, if you look in any math book, they don't refer to them as covertices at all. But I'm going to, because we need to think of this a lot like ellipses, where we have the vertices and then we have the covertices that help us to graph it. So the names for them, this one introduces one, but it's not a real good fit. So as we go through the vocab, just remember, keep thinking about which one's my major axis, what's my vertices and my covertices. So hyperbolas, two symmetrical branches is what we're going to get. Notice they pass through the vertex, which makes absolute sense, and they wrap around the foci. But the foci are now outside. These, I always think in my mind, are just like taking an ellipse and chopping it in half and turning it inside out, and you get a hyperbola. So instead of that addition, when we cut it up and turn it inside out, we subtract and we get this. And as you see here, they're talking about this distance from the foci to any point on the hyperbola. It doesn't matter if it's this one or this one. If we take this smaller piece away from this longer piece, it will equal exactly the same thing as if we did that pattern to the red one. It absolutely would. And what I did, I just did on purpose. Moved it like a parallelogram there so that you can see, hey, we could use this, and if we went back to geometry, we could do a lot of stuff to show that things are going to be congruent here. But it does work for any points on the hyperbola. So like it says, that's the structure of a hyperbola, and that difference between those two pieces, those two distances, is constant. So they look like that when they are centered at 0, 0. Well, there's no h and k. Also notice the big difference between the horizontal and the vertical is now, hey, the x's and y's have swapped position. This is x squared minus y squared. This is y squared minus x squared. Also know this, because this messes with people. A no longer has to be the biggest number. Not with hyperbolas. That's an ellipse thing. Only with ellipses. So in a hyperbola, C is going to be greater than A. And again, I always think of it this way. This formula has subtraction in it, so it makes sense that if something's missing, and I have to undo that minus, it should have addition in it. So you can always think opposite sign of what you have for the original formula. So c squared equals a squared plus b squared. Again, a is always first. There's no question of which one is bigger. It's, hey, whatever's underneath that positive term, if it's the positive x squared or the positive y squared, that's going to be what we use for a. Not required to be bigger. And down here, it all fits together just like it did when we were talking ellipses, except the foci are now outside the hyperbola, because we're wrapping around with those. Right here, you see C, and right here. I know this one is horizontal because A is on the horizontal axis, or it has to be. It has to be on the axis that you're working with. And then on this one, I see that my A values are going up and down. That's my vertical. So that must have been underneath the y squared in order to get that to happen. One new little piece that in here we're not going to use a whole lot is that we have these asymptotes that we're going to use right here. And we have little equations for these. And I've said before, I don't like to memorize. I would rather make a sketch of it and figure out how these things came to be. So if we want the slope of the asymptote, I ask myself, well, how do I get from this nice center at 0, 0 to this spot up here? Well, I would have to go up b units, because that would be my covertex. And then I'd have to go over a units, and that's rise over 1. So b over a makes perfect sense. Now, if it's vertical, when we do the math, notice this time you'd be going up a units and over b units. So it makes sense when you think about where your a's and b's are located. So why didn't they put a b on there? Again, with hyperbolas, nobody has ever said, we're going to call them this, and we're going to use b to always do this. So, like I said, I'm going to refer to them as covertices because they need to be there. They're a part of our graph, but they just don't get a fancy name as we go through any of this. So, hyperbola centered at the origin. We know those because there won't be an x minus h, there won't be a y minus k, it'll just be x squared and y squared. Some definitions. We've got a chord, that hasn't changed. We're still looking at line segment with endpoints on the hyperbola, so a chord on the hyperbola. The chord that lies on the focal axis connecting the vertices, which is length 2a. Well, with ellipses, we call that the major axis, but it's not called that. I wish the people that did conics would have kind of got together and talked about this. That's called the transverse axis with hyperbolas, which I've never been able to come up with a way to say, hey, it's this part from the original wording that tells you what it's doing. And it's just like they kind of put their name and threw it at it. So it's the transverse axis. Think of it as the major axis. It'll be totally fine. Major axis, transverse axis. And then the one with the length of 2b, the conjugate axis. Now that name kind of makes some sense because conjugate is kind of undo. So it's undoing that transverse axis. And then the number 8, semi-transverse axis. Again, the names do make sense because semi in math means 2. We talk about semi-annual interest, that means interest twice a year. So they're saying if you break that transverse axis into 2 equal pieces, you get 8. We want to think of it as vertices. So we want to think of it as. And then the number b is the semi-conjugate axis. Semi-conjugate axis. So with the ellipses, they call these the semi-major and the semi-minor. And we have some different language here as we're dealing with A and B. Like I said, when we're going through it, just think of it as vertices and covertices, and you won't have very much difference from what we did with the ellipses. You really won't until we do the actual graphic. Then things get really super cool. Alrighty, hyperbola centered at 0, 0. If you're a formula memorizer, you've seen 3 of these gigantic square rectangle pieces here with lots of formulas in it. But if we just think through them and think about what we know and realize, okay, now it's the x's and the y's that I'm looking at. So I want to know which one's positive, that should go in front. If it's x x squared, it's horizontal. If it's y squared, it's vertical. And then the rest of it, we actually would graph pretty much the same way that we have graphed A and B and C before. It's what we do with them that makes a hyperbola. What we decide to do with them that makes a hyperbola. And since hyperbolas have subtraction in the original formula, we use the plus there in order to find anything that's missing. And then the asymptotes, again, that's kind of a new piece. They don't ask for that a lot in the homework, but I'm going to try to make sure I do a couple of those at least in your notes so that you've got something where you're knowing that those are important when you do other math besides what we're going to do with the basics here. So here's where they get different. When we were making our ellipses before and we found A and B, we put them on there and then we just tried to round everything up so it looked like an A. What we're trying to find with hyperbolas is a box to give us our asymptotes. Because asymptotes, remember, are lines that we approach, but we never quite make it there. So once we know A and B, we're going to make, and it shouldn't be solid, so they shouldn't have done it solid, but they made it red to show us, hey, this is a helper thing. So we're going to make a helper box, and it should be dashed. And then we're going to draw in the asymptotes, because the asymptotes are always the diagonals of that box. And asymptotes, again, are helper lines. So there they are. Now A, remember, even though they give them fancy names, semi-transverse, are actually the vertices. So I know my hyperbola has to go through A. And I also know what asymptotes do. Asymptotes are things that we approach but never cross. So that would mean I'm going to have to make my branch of my hyperbola do that on that side. And then the mirror image of it through A on the other side. So I always thought this was really a cool process. And again, this is only for perfect situations where we have a lot of perfect squares involved in what we're doing. But it's a really cool way to get a really nice hyperbola drawn. So box, asymptotes, put in the hyperbola. That's what we need to do. Let's get started. This one says find the vertices and the foci of 4x squared minus 9y squared equals 36. So let's just say the header wasn't up there. But I'm thinking to myself, is this going to be a parabola, an ellipse, or a hyperbola? Well, then I tell myself, self, x squared and y squared. I'm down to ellipse and hyperbola. Self, there's subtraction. This is a hyperbola. So what I need to do is get that 1 by dividing all of the terms by 36. So it looks like that. All right. So now what I need to do is figure out, well, A, B, and C would be really helpful to answer any of the questions that they have here. But I do want to know whether or not this is horizontal or vertical so I can actually do those correctly. You know? So is this horizontal or is it vertical? It is horizontal. We've got the x squared minus the y squared. So this is horizontal. I already know my center. That's at 0, 0. Now I didn't see any H and K business going on up there connected to my x's and my y's where they would need to be. All right. So if it's horizontal, I need to know what A is so I can figure out where, I'm going to call them vertices, where they're at. So what's A? It is 3. There's our A squared. And since it's horizontal, that's going to mean that I'm going to need to go left 3 and right 3. So my vertices and you could certainly do plus or minus 3, 0. I want to write that shorthand. And then, if I'm going to graph it, I'm also going to need to know what B is. So what's B squared? 4. So B is what? 2. Does that go horizontally? No, that's our up and down. So, again, I'm going to call them covertices, just so we remember that as we're going through all of this. That's going to be 0, up 2, and down 2, so 0 plus or minus 2. right, they wanted the vertices. Got them. They wanted the foci. Don't got them. Formula for hyperbolas has subtraction in it. When something is missing, we use addition to find it. We already know what a squared, b squared, 9 and 4. They're right there. Ew, that's not going to be pretty. Well, it doesn't have to be. We just have to tell them where it's at. So, are the foci going to be on the same axis as the vertices or the same axis as the covertices? The vertices. They're on that transverse axis. So that's going to be, a little spot down here for foci, plus or minus the square root of 13, 0. And you can kind of think about the square root of 13. Let's see, 3 squared is 9, so not quite enough, but 4 squared is 16. So somewhere between there. And we have calculators, so we can punch that in. Alrighty, let's get all this good stuff on here. We have vertices at negative 3, 0 and 3, 0. We have our little covertices at 0 plus or minus 2. And to graph it, we don't necessarily need to put foci on there. That's where we're going to get our box, right there. So, from vertex to vertex, that's going to be the width of our box. And from covertex to covertex, that's kind of the depth of our box here. You can think of it as length times width. There's our box. What's the box for? Asymptotes. Yeah, so from diagonal to diagonal, we want to draw in some asymptotes. Oh, I went too far? Thank you. There we go. All right, so asymptotes through the diagonals. Again, dashed or dotted. They're helpers. They're not actually our hyperbola. We just made it through the hardest part. Because you know what happens every year? Somebody puts those covertices and vertices on there and makes an ellipse. It's tough because ellipses were the first thing that we learned about. You get there and you forget. Hey, this one's a hyperbola. So be careful with that. Now we're not quite done. Which way did we say these open? So they've got to go out to the right and left. And they've got to go through our vertices and approach our asymptotes, but not cross them. That's huge. Don't let them cross. Make sure you put your arrows on there to show, hey, this is going forever. Like so. Well, find the vertices and the foci. Did that. Graph the hyperbola. Did that. Well, let's go ahead and write the equation for the asymptotes. Like I said, you certainly could memorize that. But I think it's easier to look at where we have these asymptotes and say to yourself, if I go up, because it's rise over run, that's B, and that's A. So I'm going to need plus or minus B over A. B was 2, A was 3. X. So just from having even a sketch, you know, if you didn't graph the whole thing, then you could make your way through and realize it's going to be a little bit for the horizontal. So there it is, and even some stuff we didn't necessarily need. Well, we got it all. Now, if we wanted to graph the foci, like I said, we have calculators. They're not just a prop. You can find the square root of 13. And then say, all right, we're going to go about 3.6 right and left. And put the foci on. But does that help us graph the hyperbola? No. I mean, we already knew it was horizontal. We know it's going to wrap around the foci. And now we've got 2 added things on there that are just, you know, in addition to something that's already pretty complicated. So we might want to just leave those off for graphic purposes. Okay. Anything about that one we should talk about? Is that awful? Got some yeses going on with the nod there. All right, let's try this one. We're gonna write an equation now. Finding an equation and graphing a hyperbola. Find an equation of the hyperbola with foci at 0, -3, 0, 3, whose conjugate axis has length of 4. Sketch the hyperbola and its asymptotes. Well, all right, let's do that then. My first question would be, where's the center? Because without that, we can't find A and B. You know, A, B, and C all relate to the center. So, well, how'd you know? Halfway between -3 and 3. It's 0. So our center is at 0, 0. And we might want to start sketching here so we know if this is horizontal or vertical. Let's see. 0, -3, and 0, 3 are the foci. So which way does this go? It is vertical, exactly, because the vertices and the foci are always on that transverse axis, the major axis. So we need a little y squared over a squared minus x squared over b squared equals 1, with x and y have switched positions. Okay. Well, let's see what we have so far. I think we can find C at this point. What is C, the distance from the center to the focus? 3. We need more than that if we're going to find them all. Let's see. Conjugate axis. Is that the major axis or the minor axis? That's the minor. Conjugate axis has a length of 4. So that would mean we've got to go out 2 this way and 2 this way to our covertices. Well, that just told us what B is. B is 2. Now we can find A, because there's nothing else up there that tells us about A, right? So what equation should we use to figure out what A is? Yep. So 3 squared equals A squared plus 2 squared. 9 equals A squared plus 4. A squared is 5. Now, when we write it, that would be good enough. We can just put it right there for A squared. But it did say sketch it. So we probably want to figure out, our little square root of 5 as we go through it. And again, you can kind of think 2 squared is 4, 3 squared is 9, so it's going to be 4 point something. But we want to know 4 point what? We want to do this accurately. Or 2 point something. So 2.2. Again, it starts to make our drawing look really busy. Right there. Well, let's see if we have enough to at least write it, because it said find an equation. That was the first thing we were supposed to do. Do we know A squared? That was 5. Just did that. Minus x squared over, we know B squared. We actually just did that too when we were going through and doing this math to figure out what A is. And then it says sketch the hyperbola and its asymptote. So we had everything we needed to write the equation. So what do we do over there? Draw a box. Now forget about the foci when you're drawing the box. They are not part of the box. Vertices and covertices. What's the box for? Asymptotes. Here's the other thing that people mess up on. If you didn't label your dots for your covertices versus your vertices, every once in a while somebody throws them the wrong way. So, which way was this one supposed to go? Vertical, up and down. Through the vertices, not the foci. Wraps around the foci. Let's do the asymptotes while we're here. Like I said, I don't know why they just totally leave that out. We have it all labeled. You look at at this and you say to yourself, vertices, that's going to be A, covertices, that's going to be B, y equals plus or minus A, square root of 5, over B, which was 2, x. There you go. Now, problem like this on the test, you might have other slots where you write down, here's where the vertices are, here's where the covertices are. And like I said, we're probably going to refer to them as that, even though they have the special names for hyperbolas with the transverse and conjugate axis, semi-transverse and semi-conjugate. Because the y squared was first, and we knew that from knowing that the foci were on the vertical axis. So as soon as you find either the foci or the vertices, they tell you where the axis is going to be. Process of elimination, if they give you the covertices, and that's on the x-axis, you know the other two are going to be on the y-axis. Alrighty, 43210, if we just stopped here, centered at 0, 0, how would you feel about working with hyperbolas? So a little bit lower, and I expect that because now we're starting to get more information about conics. There's more things to look for and go through. So now what do we need to do? Well, we have to move them. You know, good old H and K switch here. So when a hyperbola was centered, 0, 0 is translated horizontally by H units, vertically by K units. The center of the hyperbola moves from 0, 0 to HK. Not a shocker, we've done it before. Such a translation does not change the length of the transverse or the conjugate axis. The placement, well, yeah. I mean, obviously, if we're moving this right and left and up and down. So, this box, if you take a look at it, and I would think the only scary looking thing on here would be the asymptotes. We're not going to spend a lot of time on the asymptotes for the translated figures. We're just not. But notice how it's still going to be, hey, I can get covertices over vertices. I need the H attached to the X, and then I have a K in the back to go through that translation. So it's not very different from what we did before. And the rest of this, again, just kind of comes naturally from starting a sketch, maybe drawing, and seeing where is everything. But the distance is no longer 2, 0, 0 when we're talking about B and C. It's the distance for A from vertices to the center, B from covertices to the center, and C foci to the center. So sometimes it takes a little longer to do the calculations since they're not 0, 0 anymore. So there it is. That's a scary looking drawing right there. Look at all those labels they have on everything. But that, again, is just stuff we're probably going to do in our head. You know, we're going to say, hey, if my center right here is at 3, 4, well, I'm going to have to change that 3 in order to get my vertices because it's horizontal. And the X is responsible for horizontal movements. And the Y is responsible for the vertical. So it's not like we're memorizing any of that. It looks pretty awful. But it breaks it down for us. So here's what we do. To graph or write an equation for a hyperbola from given features. Sketch and label what you're given. Get a visual. See what you have. Hopefully, it'll be enough to locate and plot the center. And it's going to be halfway between either the foci or the vertices or the covertices. Halfway. And then determine A, B, and C. Figure them out from your graph. What do you have? What are those distances? Sketch the hyperbola. Figure out which way it's going. Determine which direction. And then write the equation if you're writing. So we put all of the things that we did with ellipses into hyperbolas. This one says we're going to find an equation of a hyperbola. Move that up a little bit. And find the standard form of the equation for the hyperbola whose transverse axis has endpoints -2, -1, and 8, -1, and whose conjugate axis has a length of 8. Better make a sketch. -2, -1, and that is the transverse axis. What does that mean to us? The vertices. So vertex at -2, -1, and another vertex at 8, -1. Now before I get too much clutter on there, is that enough information to find something helpful? center. Notice how they're both -1. So we know the center is going to lie somewhere on that transverse axis. All we have to do is average the axis. That's all we have to do. So -2 plus 8 divided by 2. That's going to be 6 divided by 2, which is 3. So that means our center is at 3, -1. And that's a definite get it on the graph. I want to see that. All right, looks like so. Now that we have the center on there, I think we could find either an A, B, or a C value pretty easily. Which one? Vertices are used for A, right? So how far is it from 3 to 8? Notice I didn't even bring up the -1. Yeah, wouldn't even need that. All right, so that wasn't the only information they gave us, but we just got a lot of stuff from that piece of information. Conjugate axis. Which one's that? Like the minor axis, yeah, the covertices. Has a length of 8. Ooh, so how do I use that? 4 up and 4 down. And you could just help to figure out where they're at, or you could say to yourself, okay, so this time the 3 is not changing, but the -1, if I add 4 to that, that's going to be at 3. And that -1, if I subtract 4 to go 4 down, is going to be at -5. And I think that just helped us out. How far is it? 4, yeah, it's 4. So find the standard form of the equation. We needed a center, we needed A, and we needed B. I think we have it. So is this one horizontal or is it vertical? How do we know? Vertices, either think, okay, it's always the vertices and the foci, or you could say it's the opposite of whatever the covertices are. So which comes first, x squared or y squared? X squared. Do we know h and k? What did we find that goes in for h and k? The center. And that was our 3, -1. So this will be x minus 3 squared minus y plus 1 squared equals 1. And now our only job is to figure out what we should be putting underneath it. Do you know what a squared is? 25. What's b squared? Did it say we had to sketch the graph? No, so we could stop. You know, we could, and I get a feeling that it just 5 minutes. 5 minutes? Okay. I just vertices to covertices, asymptotes. And yeah, this one will run off a little bit because you know it's horizontal. And we don't have a lot of space over here. We can squish it in. Get that on there. Like so. So, H and K, bless you. Just kind of a natural way to go once we've had that. Now, let's see. Well, we're one short of where we need to get, but you know what? That'll give you a chance to try some tonight, and then that one should go pretty doggone fast. So now, 4, 3, 2, 1, 0, me, I'm braced for it. I'm sure they're going to be a little lower with the centers of H and K, but maybe not. Let's say now that just solidified that in there. So it looks like about the same after H and K. Okay. Let's use some of the baby hyperbola.